Dear students, welcome to the lecture on MET201 Mechanics of Solids, Module 1, Part 2, Principal Stress and Strain Displacement Relations. Myself is Dr. Manoj Tarian, Associate Professor, Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. After attending this lecture, you will get the concept of principal stress and principal plane, invariance of stress, displacement field in a body which undergoes deformation, displacement gradient metrics, strain displacement relations, strain metrics and strain tensor, analogy between stress and strain tensor, where you will get the concept of principal strains, strain invariance, and stress and strain transformation equations. Consider a body which is subjected to a number of external forces as shown in this figure. The stress state at point Q due to the external forces is found out by taking a section of the solid. The stress state at point Q with respect to the reference coordinates x, y and z is given by the matrix sigma ij. The 6 independent stress components of the stress state at point Q are sigma xx, sigma yy and sigma zz are the normal stresses, tau xy, tau xz and tau yz are the shear stresses. The stress state at point Q is shown on an infinitesimally small rectangular element at point Q in this figure. The various stress components acting on the various faces of the infinitesimally small rectangular element at point Q are shown in the figure. Knowing the stress state at point Q, the normal stress and shear stress on any arbitrarily oriented plane passing through point Q can be found out using the Cauchy's stress formula. Here, A, B, C represents an arbitrarily oriented plane passing through point Q. The normal to the arbitrarily oriented plane ABC is represented by the vector n. The direction cosines of vector n are nx, ny and nz. That is, cosine of the angle between vector n and the x direction is nx, cosine of the angle between n and y direction is ny, and cosine of the angle between n and z direction is nz. Tn represents the resultant stress vector on plane n. The components of Tn along the x direction is Txn, along the y direction is Tyn, and the component of Tn along the z direction is Tzn. Once we know the state of stress at point Q, the values for Txn, Tyn and Tzn can be found out using the Cauchy stress formula given here. After finding out the stress components Txn, Tyn and Tzn, the normal stress on plane n represented by sigma n can be found out using equation 1. That is, sigma n is equal to nx into Txn plus ny into Tyn plus nz into Tzn. The resultant stress vector Tn on plane n can be found out using the equation 2. Knowing the values of Txn, Tyn and Tzn, substitute these values in equation 2 and we get the value for the resultant stress vector Tn. Once Tn is known and sigma n is known, the value of the shear stress on plane n can be found out using the expression 3 by substituting for Tn and sigma n. This is how we find out the normal stress and shear stress on an arbitrarily oriented plane using the Cauchy's stress formula. A principal plane is defined as a plane where there is no shear stress. At point Q, the arbitrarily oriented plane A, B, C, which we have considered earlier, be a principal plane. When ABC is the principal plane, the resultant stress on this plane will act along the normal direction n. That is, the resultant stress Tn is the same as the normal stress sigma n, and the resultant stress has got no component along the plane. The components of with the resultant stress Tn, that is sigma n, along the x direction is Txn, along the y direction is Tyn, and along the z direction is Tzn. These components can be written in terms of sigma n as Txn is equal to sigma n into cosine of the angle between n and the x direction, that is nx. Similarly, Tyn is equal to sigma n into ny, and Tzn is equal to sigma n into nz. We have already seen that the stress components Txn, Tyn, and Tzn can be written in terms of the 6 independent stress components at Q as in the set of equations 2, that is the Cauchy stress formula given here. Now, if we equate the right hand side of the first and second set of equations, we will get sigma n into nx is equal to sigma xx into nx plus tau xy into ny plus tau xz into nz. Sigma n into ny is equal to tau xy into nx plus sigma yy into ny plus tau yz into nz, and sigma n into nz equal to tau xz into nx plus tau yz into ny plus sigma zz into nz. The plane n in the previous slide represents the principal plane. The normal stress acting on the principal plane is called the principal stress. The principal stress is represented by sigma. Thus, equation 3 in the previous slide can be written in the form as the set of these 3 equations. Collecting all the terms onto one side, this set of 3 equations can be written as sigma xx minus sigma into nx plus tau xy into ny plus tau xz into nz equal to 0. The second equation will become tau xy into nx plus sigma yy minus sigma into ny plus tau yz into nz equal to 0. And the third equation becomes tau xz into nx plus tau yz into ny plus sigma zz minus sigma into nz equal to 0. In this set of 3 equations, sigma represents the principal stress, nx, ny, and nz represents the direction cosines of the corresponding principal planes. Now, this set of 3 equations represents an eigenvalue problem, where sigma is the eigenvalue and nx, ny, and nz are the corresponding eigenvectors. Once the value of sigma is known, this set of 3 equations represents the set of 3 simultaneous linear equations. In order to have a non-trivial solution for nx, ny, and nz, the determinant of the coefficient matrices should be equal to 0. Thus, we get determinant of this coefficient matrix is written here equal to 0. Expanding this determinant and collecting the coefficients of sigma cube, sigma square, sigma, and the constant term, we get sigma cube minus sigma xx plus sigma yy plus sigma zz into sigma square plus sigma xx into sigma yy plus sigma yy into sigma zz plus sigma zz into sigma xx minus tau xy square minus tau yz square minus tau xz square into sigma plus sigma xx into sigma yy into sigma zz plus 2 tau xy into tau xz into tau yz plus sigma xx into tau yz square plus sigma yy into tau xz square plus sigma ZZ into tau xy square equal to 0. The last equation in the previous slide can be written in the form sigma cube minus I1 sigma square plus I2 sigma minus I3 equal to 0, where I1 is equal to sigma xx plus sigma yy plus sigma zz. That is the sum of the diagonal elements of the stress matrix. I2 is equal to sigma xx into sigma yy plus sigma yy into sigma zz plus sigma zz into sigma xx minus tau xy square minus tau yz square minus tau xz square, which is equal to the sum of the determinants of these three submatrices. It is easy to remember these three submatrices. That is, the first submatrix is obtained by eliminating the row and column containing sigma xx from the given stress matrix. The second submatrix is obtained by eliminating the row and column containing sigma yy in the given stress matrix, and the third submatrix is obtained by eliminating the row and column containing sigma zz in the given stress matrix. I3 is equal to sigma xx into sigma yy into sigma zz plus 2 tau xy into tau xz into tau yz plus sigma xx into tau yz square plus sigma yy into tau xz square plus sigma zz into tau xy square, which is equal to the determinant of the given stress matrix. Thus, the stress state at a point is known, that is, the stress matrix at a point is known. We can calculate the values of the I1, I2 and I3. Substituting these values in this equation, we can solve this cubical equation and get the values of sigma. We will get three values for sigma. Thus, for a given stress state at a point, we will have three principal stresses. This cubical equation is known as characteristic equation, and the coefficients I1, I2 and I3 are known as stress invariants for the given state of stress at a point. Solving the characteristic equation represented by equation 6, we will get three values for sigma. As already mentioned, these three values of normal stress are called the principal stress at point Q. The largest value which we obtain for the principal stress is assigned to sigma 1. The second largest value is assigned to sigma 2, and the least value is assigned to sigma 3. Thus, sigma 1, sigma 2 and sigma 3 represents the principal stress at point Q for a given stress state such that sigma 1 is greater than sigma 2, which is greater than sigma 3. You should understand that sigma 1 is the maximum normal stress at point Q for a given stress state, and sigma 3 is the minimum normal stress value at point Q for a given stress state. Once the values of the principal stresses are known, the principal stress values are substituted in equation 4. That is, these set of three equations, we will get three simultaneous linear equations with the unknowns nx, ny and nz. Also, we can make use of the equation nx square plus ny square plus nz square equal to 1 in order to solve for nx, ny, nz. Thus, for each of the principal stress, say for sigma 1, we will get a set of values for nx, ny, nz, which is named as nx1, ny1, nz1. This represents the direction cosines of principal plane where the normal stress is sigma 1. Also, corresponding to sigma 2, that is, by substituting the value of sigma 2 in this set of equations, we will get the direction cosines of the normal to the principal plane 2, that is nx2, ny2 and nz2. And substituting this sigma 3 value in this set of 3 equations, we will get the values of nx, ny, nz as nx3, ny3 and nz3, which represents the direction cosines of the normal to the principal plane 3. Thus, for a given state of stress, we get the principal stress values and the corresponding principal planes represented by these direction cosines. As I have already told you, sigma 1 represents the maximum normal stress at point Q for a given state of stress, and sigma 3 represents the minimum normal stress at point Q for a given stress state. The maximum shear stress at point Q is given by tau max is equal to sigma 1 minus sigma 3 divided by 2. Now, for the principal planes, we have these following properties. That is, the three principal planes are mutually perpendicular. The angle between the principal plane and the plane of maximum shear stress is 45 degrees. Now I'll explain to you why I1, I2 and I3 are called stress invariants. Consider the stress state at point Q in a body for a given set of loading. The stress state be represented by sigma xx, sigma yy, sigma zz, tau xy, tau xz and tau yz with reference to coordinates x, y and z. So these are the coordinates x, y and z. Now consider a transformed set of coordinates x dash, y dash, z dash. That is a set of reference coordinates which are mutually perpendicular but is having a different orientation as compared to x, y, z. The stress state at the same point Q with reference to the transformed coordinates x dash, y dash, z dash on the same body for the same set of loading is given by sigma x dash, sigma y dash, sigma z dash, tau x dash, y dash, tau x dash, z dash and tau y dash, z dash. When you calculate the stress invariance I1, I2, I3 using this stress state, and also when you calculate I1 dash, I2 dash, I3 dash using this transformed stress state, both these values will be the same. That is why I1, I2 and I3 are called stress invariants. That is, I1 is equal to I1 dash, I2 is equal to I2 dash and I3 equal to I3 dash. Now we will see why they are invariant. Using the stress invariance I1, I2, I3, we will get this characteristic equation, that is sigma cube minus I1 sigma square plus I2 sigma minus I3. As I have already told you, solving this characteristic equation will give you the principal stress at point Q for the given loading for a given structure. Solving this characteristic equation, that is using this stress invariance, when you solve this characteristic equation, this also will give you the three principal stress at point Q for a given set of loading and for the given geometry. You should understand that the principal stress value does not depend upon the reference coordinates. It depends only on the geometry of the structure and on the external load. That is, the maximum normal stress, the minimum normal stress depends only on the external loading and the geometry of the structure. It does not depend upon the reference coordinates, which means that these two equations should give the same values for the principal stress. It is possible only when I1 equal to I1 dash, I2 equal to I2 dash, I3 equal to I3 dash. Thus, the values of the stress invariance does not depends upon the reference coordinate you take. Now we will see an example. Find the principal stress and the principal plane for the following state of stress. The state of stress is given by the matrix 1, 2, 1, 2, 2 minus 3, 1 minus 3, 4 megapascal. The stress invariants are obtained. I1 is equal to sum of the diagonal elements, which is equal to 7. I2 is equal to sum of the determinants of the submatrices, which we will get it as 0. I3 is equal to determinant of the given stress matrix, which we will get it as minus 31. So the characteristic equation becomes sigma cube minus 7 sigma square plus 31 equal to 0. Solving this cubical equation, we will get three values for sigma as 6.19, 2.68, minus 1.87. 6.19 megapascal being the highest value is assigned to sigma 1. 2.68 megapascal, the second largest value, is assigned to sigma 2, and the least value minus 1.87 is assigned to sigma 3. Thus, the three principal stresses at the given point is found out. Determine the direction cosines of principal planes. We will start with principal plane 1, where sigma is equal to sigma 1 is equal to 6.19. So this value of sigma we will substitute in this set of three equations. The values of sigma xx, sigma yy, sigma zz, tau xy, tau xz, tau yz are substituted from the given stress matrix. We will obtain this set of three equations, that is, this minus 5.19 is equal to the given value of sigma xx minus 6.19. This minus 4.19 is the given value of sigma yy minus 6.19, and this minus 2.19 is equal to sigma zz minus this 6.19. This 2 represents tau xy, 1 is tau xz, minus 3 is tau yz. Thus, we obtain the set of these three equations. Now, we can write the coefficient matrix for this set of three simultaneous linear equations as shown here. Now, in order to solve for nx, ny, nz, since nx square plus ny square plus nz square equal to 1, we can make use of the cofactors in order to solve for nx1, ny1 and nz1. We will calculate the constants a1, b1, c1 for this given coefficient matrix. Here a1 represents the cofactor of the first element in the first row, first column, that is element whose I is equal to 1, j is equal to 1. b1 represents the cofactor of this element, that is the element for which I is equal to 1, that is the row number, and j is equal to 2, column number. C1 here represents the cofactor of this element, that is for the element whose I, that is row number, is equal to 1, and j, that is the column number, is equal to 3. Now, the cofactor a1 is equal to minus 1 whole raised to I plus j. For a1, for this first element, I is equal to 1, that is row number equal to 1, and j is equal to 1, that is column number is equal to 1. That is how you get minus 1 whole raised to 1 plus 1 into the minor of this element, which is obtained by removing the row and column containing this element. We will get determinant of this submatrix. that is determinant of minus 4.19, minus 3, minus 3, minus 2.19. When you calculate this, you will get A1 is equal to 0.176. The general formula for the cofactor of an element is minus 1 whole raised to I plus j, where I is the row number of the element, j is the column number of the element, multiplied by the minor of that particular element. Minor of this, say for example, this particular element is obtained by removing the row and column containing that particular element. That is, the four elements represents the minor of this element. Now applying the same for finding the cofactor of the second element here, you will get B1 is equal to minus 1 whole raised to 1 plus 2. 1 is the row number for this particular element, 2 is the column number for this particular element, that is minus 1 whole raised to 1 plus 2 into minor of this second element. That is, by removing this row and column, we will get the minor as 2 minus 3, 1 minus 2.19. When you calculate, we will get the value of B1 as 1.38, and C1, the minor of this element, is obtained by minus 1 whole raised to 1 plus 3, where 1 represents the row number for this element and 3 represent the column number for this element, into the minor of that particular element, which will be these four elements, which you will get it as C1 is equal to minus 1.81. Then the value of nx1 is equal to a1 divided by square root of a1 square plus b1 square plus c1 square, which is equal to 0.0771. ny1 is equal to b1 divided by square root of a1 square plus b1 square plus c1 square, which is equal to 0.6045, and nz1 is equal to c1 divided by square root of a1 square plus b1 square plus c1 square, which you will get it as minus 0.7928. So these three values represents the direction cosines of the normal to the principal plane 1. In the same manner, we can find out the direction cosines of principal plane 2, that is where sigma is equal to sigma 2 equal to 2.68. You substitute this 2.68 in the set of these three equations. We will get these three simultaneous linear equations with the three unknowns nx, ny, nz. This is the coefficient matrix. We can calculate the cofactors a1, b1, c1, and in the same way as earlier, we can find out the direction cosines nx2, ny2, nz2, which are the direction cosines of the normal to the principal plane 2. Also, here I have calculated the direction cosines for the principal plane 3, where sigma equal to sigma 3 is equal to minus 1.87. We substitute this value of sigma 3 equal to minus 1.87 instead of this sigma in the set of three equations. We will get these three set of simultaneous linear equation. This is the coefficient matrix. Calculate the cofactors a1, b1, c1, and we get the direction cosines of the principal plane 3. Now we have written here the answers, that is the principal stresses and the corresponding principal direction. We have the first principal stress sigma 1 equal to 6.19 megapascal. The direction cosines of principal plane 1 are 0.0771, 0.6045 and minus 0.7929. The principal stress sigma 2 is equal to 2.68 megapascal, and the direction cosines of the normal to the principal plane 2 are minus 0.7872, minus 0.4486 and minus 0.4231. The value of the principal stress sigma 3 is equal to minus 1.87 megapascal, and the direction cosines of the normal to the principal plane 3 are 0.6117, minus 0.6573 and minus 0.4401. I will explain to you the concept of displacement in the case of a three-dimensional body. Consider a body as shown in the figure. The solid line shows the shape of the body before deformation, and the dotted line shows the shape of the body after deformation. In order to study the deformation or change in shape of a body, we compare the position of a material point in the body before and after deformation. Now consider a point P, whose coordinates are x, y, and z on the body before deformation. After the deformation, the point P will take a new position P dash, whose coordinates are given by x dash, y dash, and z dash. Vector P dash is called the displacement vector at point P. It is denoted by capital letter U. The vector U has components small letter u along the x direction, small letter v along the y direction, and small w along the z direction. When we say that the displacement field is completely defined throughout the body, it means the displacement u of any point belonging to the body is known once its coordinates are known. Now we will see an example for the displacement field. For the body shown in the figure, the displacement field is given by u is equal to x square plus yi plus 3 plus zj plus x square plus 2yk. Now consider a point P whose coordinates are 3, 1 and -2. In order to find out the displacement at point P during the deformation, we substitute the coordinate values of P in the displacement field vector u, and we get u is equal to 3 square plus 1i plus 3 minus 2j plus 3 square plus 2 into 1k. That is, u is equal to 10i plus j plus 11k. This means that point P during the deformation will get displaced by 10 units along the x direction, 1 unit along the y direction, and 11 units along the z direction. The initial position vector r of point P is given by r is equal to 3i plus j minus 2k. After the deformation, point P will take a new position P dash. Thus, the final position vector r dash of point P dash is given by r dash is equal to r plus u. That is, to the initial position vector of r, we add vector u, and we get r dash is equal to 13i plus 2j plus 9k. This means the coordinates of point P dash is given by 13, 2 and 9. Thus, during the deformation, a point P whose coordinates was 3, 1, minus 2 takes a new position P dash whose coordinates are 13, 2, 9 as per the given displacement field. Now we will see another example where we consider 2 points P and Q. We will see the distance between points P and Q before deformation and after deformation. Let the coordinates of P be 0, 0, 1 and that of Q be 2, 0, minus 1 in the undeformed body. Using the distance formula in the coordinate geometry, we can find out the distance between P and Q as d is equal to 2 root 2. Let capital U is equal to x square plus y times I plus 3 plus z times j plus x square plus 2y times k be the displacement field in the body. The displacement vector at point P is obtained as, that is, the displacement vector u at point P is equal to, by substituting the coordinates of P in the given displacement field, we will get it as 4j. That is, the displacement components at capital P are along the x direction u is equal to 0, along the y direction v is equal to 4, and along the z direction w is equal to 0. The final coordinates of P after the deformation, that is, after deformation P takes a new position P dash, and its coordinate values are obtained by adding these displacement components to the original coordinates of P, and we obtain the coordinates of P dash as 0, 4 and 1. Similarly, the displacement components at Q we obtain by substituting the coordinates of point Q in the given displacement field, and we will get small u along the x direction is 4, v along the y direction is 2, and w along the z direction is 4. The new coordinates of point Q, that is, at the new position of Q is Q dash, and we obtain its coordinates by adding these displacement components to the original coordinates of Q, and we obtain the coordinates of Q dash as 6, 2, 3. The distance between P dash and Q dash we obtain using the distance formula, that is d dash is equal to 2 root 11. Here I will introduce you to the concept of displacement gradient matrix. Consider a point P whose coordinates are x, y, z in a body. Consider a small region surrounding the point P, and Q be a point adjacent to P whose coordinates are x plus delta x, y plus delta y, and z plus delta z. The displacement vector at point P be capital U, whose components are small u along the x direction, small v along the y direction, and w along the z direction. Thus, we get the coordinates of point P dash after deformation as x plus u, y plus v, and z plus w. The displacement vector at capital Q be u plus delta u. The displacement vector at Q will have components u plus delta u, v plus delta v, and w plus delta w. If point Q is very close to point P, we can use the first order approximation, that is, delta u is equal to dou u by dou x into delta x plus dou u by dou y into delta y plus dou u by dou z into delta z. That is, dou u by dou x gives the rate of change in u along the x direction multiplied by the distance between P and Q along the x direction is delta x, plus the rate of change of u along the y direction multiplied by the distance between P and Q along the y direction delta y, plus dou u by dou z, which is the rate of change of u with respect to z direction multiplied by the distance between P and Q along the z direction, which is delta z. Similarly, we obtain delta v is equal to dou v by dou x into delta x plus dou v by dou y into delta y plus dou v by dou z into delta z, and delta w is equal to dou w by dou x into delta x plus dou w by dou y into delta y plus dou w by dou z into delta z, and we obtain by adding these displacement components to the original coordinates of Q. We obtain the coordinates of Q dash as x plus delta x plus u plus delta u, y plus delta y plus v plus delta v, and z plus delta z plus w plus delta w. The components of line PQ are obtained by taking the difference between the coordinates of Q and the coordinates of P, and we obtain the components as delta x along the x direction, delta y along the y direction, and delta z along the z direction. Similarly, the components of line P dash Q dash are obtained as delta x plus delta u along the x direction, delta y plus delta v along the y direction, and delta z plus delta w along the z direction. When we define the strain at a point, we require the change in length along the x direction, along the y direction, and along the z direction. And here we see it will involve delta u, delta v, and delta w, which contains the terms dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, etc. And these terms are called gradient of displacement components at point P. The gradient of displacement components can be written in the form of a matrix as dou ui by dou xj is equal to dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, dou v by dou y, dou v by dou z, dou w by dou x, dou w by dou y, dou w by dou z. This matrix is known as displacement gradient matrix. Here ui takes the values u, v and w in turn, and xj takes the values x, y and z in turn. The strain matrix at a point is defined by epsilon ij is equal to matrix epsilon xx, gamma xy, gamma xz, gamma xy, epsilon yy, gamma yz, gamma xz, gamma yz, epsilon zz. These strain components can be obtained once we know the displacement field in a body. The strain components are given by epsilon xx is equal to dou u by dou x, epsilon yy is equal to dou v by dou y, and epsilon zz equal to dou w by dou z. Gamma xy is equal to dou u by dou y plus dou v by dou x. Gamma xz is equal to dou u by dou z plus dou w by dou x, and gamma yz is equal to dou v by dou z plus dou w by dou y. These relationships are called strain displacement relations. The strain components epsilon xx, epsilon yy and epsilon zz are called the linear strain components, and gamma xy, gamma xz, gamma yz are called the shear strain components, which is analogous to normal stress and shear stress. The strain displacement relations are also called Cauchy strain displacement relations. The 6 strain components given above are called rectangular strain components or strain components in Cartesian coordinates. Now, the strain tensor can be obtained at a point if you replace gamma xy by half gamma xy, gamma xz by half gamma xz, and gamma yz by half gamma yz. So this matrix represents the strain tensor at a point, whereas this matrix represents the state of strain or strain matrix at a point. Here is an example where the displacement field in a body is given and we are asked to find out the strain tensor or the strain matrix at point whose coordinates are 1, 2, 3. So for the given displacement field, the displacement components small u is equal to x square plus y square plus 2, small v is equal to 3x plus 4y square, and small w is equal to 2x cube plus 4z. The strain components can be found out using the strain displacement relations. Epsilon xx is equal to dou u by dou x, taking the derivative and substituting the coordinate values 1, 2, 3, we will get epsilon xx is equal to 0.002. Similarly, epsilon yy we will obtain it as 0.0016, epsilon zz equal to 0.0004. Gamma xy is equal to 0.0007, gamma xz is equal to 0.0006, and gamma yz equal to 0. Thus, the state of strain or strain matrix at the given point is written as this matrix, and the strain tensor can be obtained by replacing this gamma xy by half gamma xy, this gamma xz by half gamma xz, and the gamma yz by this half gamma yz. So thus this matrix gives the strain tensor at the given point. For the analogy between the stress and strain tensor, analogy 1, sigma ij represents the stress tensor at a point P. Analogous to this, we have the strain tensor represented by epsilon ij. Here the off-diagonal elements epsilon xx, epsilon yy and epsilon zz represents the linear strain at point P, and the off-diagonal elements represents the shear strain components at point P. In the case of stress, we have the equality of cross shear. Analogous to this, we have in strain also equality of cross shear, that is gamma xy is equal to gamma yx, gamma xz is equal to gamma zx, and gamma yz is equal to gamma zy. Analogy 2, suppose if the stress state or the stress tensor at a point P is given, the normal stress on plane n which passes through point P, whose direction cosines are nx, ny and nz, is given by this equation: sigma nn is equal to sigma xx nx square plus sigma yy ny square plus sigma zz nz square plus 2 tau xy into nx into ny plus 2 tau xz into nx into nz plus 2 tau yz into ny into nz. Analogous to this, Suppose if the strain tensor at a point P are given, the linear strain along the direction PQ having direction cosines nx, ny and nz is given by epsilon PQ is equal to epsilon xx nx square plus epsilon yy ny square plus epsilon zz nz square plus gamma xy into nx into ny plus gamma xz into nx into nz plus gamma yz into ny into nz. Analogy 3 is the analogous between principal stress and principal strain. If we are given the stress tensor at a point, we can find out the stress invariance I1, I2 and I3 using these relations. Substituting the values of I1, I2 and I3 in the characteristic equation for principal stress, sigma cube minus I1 sigma square plus I2 sigma minus I3, solving this cubical equation, we will get the three values for the principal stress, namely sigma 1, sigma 2 and sigma 3. Substituting these three values in this set of equations in turn will give you the values of the direction cosines nx, ny and nz of the three principal planes for stress. Analogous to this, if we are given the strain tensor at a point P, we can find out the strain invariance, namely J1, J2 and J3 using these equations. Substitute the values of J1, J2 and J3 in the characteristic equation for principal strain, namely epsilon cube minus J1 epsilon square plus J2 epsilon minus J3 equal to 0. Solving this cubical equation, we will get the three values for the principal strain, namely epsilon 1, epsilon 2 and epsilon 3. Substitute these values of principal strain in this set of equations and solve for nx, ny and nz. We will get the direction cosines for the normal to the principal plane for strain. It should be noted that the principal plane for stress and the principal plane for strain are one and the same. The fourth analogy is the analogy in the case of transformation equation. Consider a coordinate system x, y, z. X dash, y dash, z dash represents a transformed set of coordinate system. With respect to the x, y, z coordinate system, sigma x, y, z is the stress state at point Q, and with respect to the transformed set of coordinates, sigma x dash, y dash, z dash is the stress tensor at point Q. There exists a definite relationship between sigma x, y, z and sigma x dash, y dash, z dash. That is, we can, if we know the stress tensor sigma x, y, z, we can find out the stress tensor corresponding to the transformed coordinates using the relation sigma x dash, y dash, z dash is equal to alpha transpose sigma x, y, z alpha, where alpha is the direction cosine matrix given here, where nx x dash is the cosine of angle between x and x dash, ny x dash is the cosine of angle between y and x dash, and so on. The analogous relationship in the case of strain is epsilon x dash, y dash, z dash is equal to alpha transpose epsilon x, y, z into alpha, where epsilon x dash, y dash, z dash is the strain tensor with respect to the transformed coordinate system x dash, y dash, z dash, and epsilon x, y, z is the strain tensor with respect to the original coordinate system x, y, z.